Bhargav's third lecture. As you can see, it's on p-adic Riemann-Hilbert correspondence.
Thanks. Thank you. Thanks a lot for coming to the third lecture. So I want to, the title of the talk is p-adic Riemann-Hilbert correspondences. And this is something that Jacob Lurie and I have spent many years talking about now. And we finally have a theorem which has a nice application. So I thought I would talk about it. And so I want to begin with the application. And so maybe in the first 20 minutes or so, I will talk about the application, which is something I mentioned in the first talk. I'll elaborate a little bit more. And then I'll try to explain why Riemann-Hilbert is necessary for this kind of application. And then at the end, I will try to connect it with things in characteristic zero that people might have seen in Hodge theory. And okay, secretly, the goal of this talk is to more or less convince algebraics that the notion of perverse sheaves is extremely helpful for problems in algebra. So that's where I'm going. Okay, so let me begin with some background over the complex numbers first. So I want to explain a vanishing theorem in mixed characteristic. And so I will do that by first telling you what the vanishing theorem I'm trying to generalize to mixed characteristic is. And so it's Kodaira vanishing. And so it's one of the sort of most classical and most useful vanishing theorems in complex algebraic geometry. And it's a fairly simple statement. So here's the statement, or here's one version of the statement. So let's say X is a smooth projective variety of the complex numbers, usual complex numbers. L is an ample line bundle. So it could just be the tautological bundle from projective space pulled back. And then the vanishing theorem is that hi of X, tensor the inverse of the line bundle, is equal to 0 for I less than the dimension of X. So it's a purely algebraic statement about this bundle, saying it has no cohomology until you hit the top degree. But the proof of this theorem sort of goes through Hodge theory, and I'm not aware of sort of a direct proof. To me, it's somehow a reflection of, well, it's a combination of two facts. It's a combination of the classical fact, which I learned from Arden's work, but it's probably just Morse theory, that if you have an affine variety, it has no cohomology above the dimension rather than twice the dimension. And Hodge theory, which allows you to translate that topological fact into an algebraic fact. And so let me just give you a very, very quick sketch of what goes into the proof in some very special case, just to sort of illustrate what these ingredients are. So let me assume that L is very ample, meaning it's actually the pullback of the topological bundle from projective space. In particular, you have sections. And so H is going to be a hyperplane section in the linear system defined by L. And then in this case, Hodge theory tells you that there's a topological way of realizing what this cohomology group is. So Hodge theory says that hi of X, comma L inverse is actually a direct sum end. Well, it gives you a more precise statement, but this is all I need. So it's a direct sum end of the ith compactly supported cohomology of X minus the hyperplane section with complex coefficients. Again, this is somehow intuitively, at least it kind of makes sense. Like H is the zero locus of a section of L. And so L inverse is like the ideal sheaf of H. And so this, in some vague sense, looks like you're trying to understand functions that vanish on the hypersurface. And compactly supported cohomology has to do with cohomology classes that vanish when you restrict to the hypersurface. So there's some philosophical connection there, which can be made precise to this direct sum end statement. And so this is true for every I. And on the other hand, Arden vanishing, or whatever you prefer to call it, will tell you that this compactly supported cohomology of X minus H is actually 0 for I less than the dimension. And the reason for this is X minus H is smooth. So compactly supported cohomology is dual to usual cohomology. And for usual cohomology, it's a classical fact, which is ardent vanishing, that the usual cohomology of an affine variety will vanish about above its dimension rather than twice the dimension. So even though it's a complex variety of dimension d, its cohomology vanishes above degree d rather than 2d. And so you just combine these two to get the conclusion. So.
Is that ardent vanishing sharp in the sense that?
Yeah. I mean, it definitely does not vanish at the dimension.
Okay.
In general, I mean, for examples, it might vanish.
Yeah, because it's not quite doubling, because an open manifold or an open thing like that has cohomology vanishing in 2n already because it's open. So
no, but this is compactly supported cohomology.
Oh, complexly. Okay, fine. Correct.
So it's sort of in the other half, yeah.
Okay, fine. No, but oh, compactly supported cohomology.
Like for affine n space.
That's the same as homology, though, in the dual dimension.
Oh,
wait. Okay. Sorry, I got to think. So never mind.
Right. There's a bunch of different theories that are all the same because x minus h is smooth, and what you said might be correct. I'm not sure right now.
Doesn't matter.
Right. So what I want to emphasize is, so there's this kind of crucial ingredient coming from Hodge theory that's allowing you to translate this purely algebraic problem into something about topology. And then you can use certain ingredients in topology to get the vanishing that you want. And so now the goal of my talk is to explain how to do something similar when you're not in characteristic 0. So you don't have Hodge theory available. And there's going to be some sort of caveats because it doesn't literally work the same way. So let me maybe first make a remark on this. So first remark is that this Carrera vanishing theorem, KV, is not true in characteristic phi. So if I just take literally the same statement, but don't assume that my ground field is the complex numbers, I do it over like a finite field, say, then there are examples we know that tell you that the conclusion is just false. Those groups can be non-zero. And so you need to find a better fix.
And which cohomology are you using then?
Well, so this cohomology is just algebraic cohomology of coherent sheaves. So it makes sense in any setting.
Okay.
It's computed via check complexes. So you cover x by affine varieties and then just take sections over the affines.
Is it consistent with prismatic?
Well, the game will be to try and use prismatic to relate this coherent cohomology to something more topological.
Okay, fine.
It's also not true in mixed characteristic. Well, let me write it this way. And probably not in mixed characteristic. So this is slightly embarrassing, but I just realized recently that no one's written down a counterexample to literally the same statement in mixed characteristic. I'm sure it's false. There are slight refinements of Carrera vanishing called Kawamata-Vivek vanishing, and there are counterexamples to those statements. So I think it's just like, you have to sit down and do it, but I don't think anyone has done it yet. But I think the work to the person to ask is Totaro. So I'll put his name there. He's thought about these questions. And then the second remark I wanted to make was why this kind of theorem is useful in sort of problems in algebra. So it's often useful because cohomology groups control the obstructions to lifting solutions from a hypersurface to an ambient space. And so a vanishing of a certain cohomology group will help you solve the lifting problem. And so let me just say one way you might use it. So theorem KV implies that if H, again, as before, is a hyperplane section, then the restriction map, so you can look at sections on the ambient variety of the canonical bundle of the variety with poles of order 1 along the hypersurface. You can take then the residue and you get a differential form on the hypersurface. And then the statement is that Carrera vanishing will tell you that this map is surjective.
Can you
So
say
this
in
is-
large what those two groups are? I couldn't quite follow it.
Oh, sorry. So omega x is the canonical bundle. So the top wedge power of the bundle of one forms.
Okay.
And then I'm allowing poles of order 1 along the hypersurface.
Oh.
And this is the same thing for the hypersurface.
And that's the residue map.
Mm-hmm. And so the statement is that this map is actually surjective. And so you can imagine that if you're trying to solve some geometric problem that involves constructing sections of the canonical bundle, and you've sort of found sections here, then this surjectivity can be useful because then you can actually lift them to sections here. And this trick shows up a lot in various applications.
Do you want X to be I mean, what if H1 of omega is non-zero?
So wait, did I do this wrong? So H1, so
Maybe you need 2H, omega H plus H or something.
Sorry, you're saying my kernel term is H1 of omega. So I wanted to twist everything down by H maybe.
Yeah, and add an extra H.
Sorry. So you're saying put a 2 over here and H over here.
Yeah, that looks better.
Yeah, that looks better, sorry. Right, because the obstruction lives in H1 of omega twisted by H then. And that is their dual to H d minus 1 of minus H, which is the setting of Carrera. Yeah, thank you. Right, which actually brings me to what I'm about to say. So if you want to see why this stuff is actually useful in algebra problems, I'm not going to really spend time on it in this talk, but Carl Schweid gave a really nice talk in the Zoom algebraic geometry seminar just on Tuesday. And so the first 30 minutes of his talks are basically about trying to explain how you might use this kind of result in practice. And so I suggest looking there.
The algebraic geometry where?
Zoom algebraic geometry seminar, ZAG.
Okay.
Okay, so that was the vanishing theorem I want to focus on. And so the goal is to try and explain a version of this theorem in mixed characteristic. And so now let me sort of move there. So Carrera vanishing in mixed characteristic. And here it'll actually be useful to sort of try and formulate so I'll formulate the version of Carrera vanishing mixed characteristic, but there's a kind of a pure local algebra version of this vanishing theorem, which is often useful as to first think about. So if you think about, if you're in the setup but you have a smooth projective variety and an ample line bundle, you can think about the affine cone over the projective variety. And then sort of, it's a well-known principle in local algebra that sort of the commutative algebra properties of this affine cone reflect the cohomological properties of X. And so you'll very quickly see that Carrera vanishing is closely related to when this affine cone has the property of being Cohen-Macaulay. At least like it's useful in proving that the affine cone is Cohen-Macaulay in some situations. And so I want to talk about the local algebra version of the mixed characteristic statement as well. And so I want to first recall the notion of a Cohen-Macaulay ring before I formulate the theorem. And it's a simple notion, but I'll just write it down so that everyone's on the same page. So recall, if you have a Noetherian local ring, then it's Cohen-Macaulay. So this is the niceness property of the ring. It's a condition on the singularities, if you like. There are various ways to say it. Probably the most elementary way of saying it is that every system of parameters.
Bhargav, maybe I'm the only one with this problem, but I don't see any more writing on the. Oh, okay, sorry, it reappeared. Sorry.
Okay, yeah, please tell me if something breaks.
No, I'm okay personally right now. Okay, sorry.
We all had it, I think, Mark.
I see. Okay. So every system of parameters is a regular sequence. So if you're thinking geometrically, then what this is saying is that if you have a Noether normalization, so a finite map from from the spectrum of R to affine space, then the map is automatically flat. So it has some nice commutative algebra properties. But there's another way to say it, which is more cohomological, which is useful in applications, which is that if you look at the local cohomology of the ring that supports at the maximal ideal, this is 0 for I less than the dimension of R. So it's kind of like saying that from the eyes of coherent cohomology, the link of this singularity. So if you think of spec R as a singularity and then you remove the singular point, so remove the close point, then it kind of looks like a sphere. So it's saying that there's no cohomology until you hit the top degree, but only from the eyes of coherent cohomology.
So I know what a regular sequence is, but I don't know what a system of D parameters is.
So a system of parameters is just D. If the dimension of the ring is D, then a system of parameters is a length D sequence with the property that when you mod out by the sequence, you get something 0-dimensional.
You get something what?
0-dimensional.
Okay.
So the ideal generated by the sequence contains some power of the maximal ideal.
Okay.
And maybe sort of, yeah, okay, I'll just leave these two definitions up here.
So it's sort of related to Poincare duality, I thought, Cohen-Macaulay.
Right, so okay, I was not about to write this, but I will say part C is that the dualizing complex is actually a dualizing sheaf. So, it's actually in single degree.
Oh, that's cool.
Right. If it was actually invertible in that degree, then I think it's closer to Poincare duality. This is not quite all the way there. So that's the property of being Gorenstein. Okay, so there's this property of being Cohen-Macaulay, and then here's kind of the main theorem that I want to explain. So this is, I will call it Theorem Cm, just for ease of reference. And I'll formulate two versions of the theorem. One is in local algebra, and one is kind of a global version similar to Kodaira vanishing that I had before. So the local version is the following. So let's say R is an excellent Noetherian domain. So if you don't know what excellence is, just ignore it. I mean, it's a niceness condition that's always going to be satisfied unless you go looking for examples where it's not satisfied. They're kind of hard to come by. R plus is the absolute integral closure of R. And so what this means is you take R and you look at its integral closure in an algebraic closure of its fraction field. So it's some humongous object, right? Like even if R was like Z, this gadget over here would be something like the ring of integers in Q bar. It's some huge non-Noetherian ring, but it's just some systematic way of keeping track of all possible finite extensions at once rather than sort of fixing one of them. So it's a bookkeeping device. And then the theorem is that this gadget, R plus, is Cohen-Macaulay at all points of characteristic P. Meaning in the definition of Cohen-Macaulay over here, I was assuming I was in a local ring. And so to say that a point has characteristic P means that the maximal ideals I look at have to contain a prime number P. So if you think geometrically, you have spec R sits over spec Z, and I'm only looking at the points that sit over the close points of spec Z, not over the generic point of spec Z. And so what this is saying is that this property of being Cohen-Macaulay, it's not going to be true for R necessarily itself, but the failure of the property to be true can be killed when you go up to a finite cover. So it's some kind of a vanishing theorem up to finite covers for the property of being Cohen-Macaulay. And that's more or less the best you can expect, because I mean, it's not true on the nose always. And then there's the corresponding global version, which maybe looks more familiar from the Kodaira vanishing discussion, which is the following. So let's say V, well, let me just do it in a simple case. So let's say I work over ZP. So X over ZP is a proper flat, is a technical term, just ignore it, proper flat scheme of relative dimension D. L is going to be, so this was going to be the version of Carrera vanishing. So in there I had an ample line bundle, but we can sort of allow slightly more things. So it's semi-ample and big. This is flexibility is useful in applications, but again, there's no sort of, not much is lost if you just assume L is ample. Yeah, and then the theorem is that there exists a finite cover, possibly branched, pi from y to x, such that pull back along pi, so pi upper star kills the following groups. So there's a bunch of different cohomology groups that are going to be killed when you do this. So first is the cohomology of the structure sheaf in degrees bigger than 0. Well, the torsion part of it. I mean, that's the only part you can expect to kill. It stopped writing again, did it? Oh, no, it's there. Okay. The second statement is that the cohomology in positive degrees of the line bundle itself. And then the third part finally is the version of Carrera vanishing, which is cohomologies in degrees less than the relative dimension of the inverse of the ample line bundle. And so let me just emphasize that this is analog of Carrera vanishing. Right, and so what it's saying is that if you see these kind of spurious cohomology classes that should not be there, because if Carrera vanishing were true, then you can always find some finite cover where those classes die. So after you pull back to that finite cover, you can sort of keep solving your geometric problem that you were originally trying to solve. Okay.
Bhargav, what is the subscript with the torsion? Why is that there?
You can only kill torsion classes this way because there's a characteristic 0 problem. Like over the complex numbers, if you had a bad singularity, and Carrera vanishing was not true. Like I didn't make any assumptions on X over here, right? It was any proper flat scheme. Mm-hmm. So the generic fiber could be something horrible. And I could have some classes in there which are non-zero on the generic fiber. And then you cannot kill them with finite covers. Like in characteristic 0, you cannot kill coherent cohomology classes with finite covers if the base is normal, because there's a trace map backwards and the composition is multiplication by the degree. And so there's a characteristic 0 obstruction, and putting torsion there is a way of getting around the characteristic 0 obstruction. There's a sort of finer statement you can make that not only can you kill the torsion classes, you can also make every class divisible by p in a finite cover. So somehow p-adically, the classes are becoming smaller as you go up.
So these things are like finitely generated modules over ZP in that case, and then so it's torsion in that sort of sense, right?
Right. Yeah.
Okay. Okay, thanks.
Mm-hmm. Okay. So I want to sort of explain a little bit more about what this theorem is about and where it came from. So maybe actually before I scroll past this page, other questions about the statement? Other questions?
Why do you call it CM? Because you don't have that in the hypothesis.
Well, somehow I have it in the conclusion. It's a Cohen-Macaulay-Innes result for R+. That's how I'm thinking of the theorem.
And then, okay. And the statement ABC is for Y.
Yeah, all pi upper star, the image of these elements in the corresponding cohomology groups for Y are 0.
Oh, the image, I see.
Right, so yeah, that's an important point. You will never find a single Y where these groups are actually 0, again, because of this characteristic 0 obstruction. But if you have a fixed element you're trying to kill, you can always do it. There might be new things that are created, but often they don't sort of cause problems. I mean, sometimes they do, obviously, but for some applications, this is good enough.
I see. So for the individual Y, the same group may not be 0.
Correct.
The image from X is 0. I see.
Right.
So for example, if you, oh, okay, no.
So maybe I'll give one example as an exercise, which is going to be useful in thinking about this theorem. But maybe before I do that, I want to make a remark about the theorem first. So first of all, right, this is something I already said, but let me emphasize this. So Theorem Cm, both versions of the theorem are false in Kersig 0. The first version, I mean, they're both false for the same reason, which is that if you have a bad singularity in Kersig 0, you cannot make it better by passing to a finite cover. You're just stuck there. And so this is really kind of a mixed characteristic or a Kersig P phenomenon. The second remark is that the Kersig P versions of these theorems, so not the mixed characteristic versions, but rather the versions which are in characteristic P, were actually known before. So Kersig P versions are essentially due to Hochster and Hunicke from the 90s. And it sort of explains, there's a subject of F singularity theory, and these versions are, the Hochster-Hunicke results are extremely useful in sort of just setting up that subject. And they have sort of many applications, and part of what some of us are doing these days is trying to sort of find mixed characteristic versions of those applications now. Remark 3 is, right, this is the thing I said in the first talk, but I'll write it again. So this theorem is useful. So plus a fancier version, so a relative version, which I'm not going to spell out here. It was useful in the same way that Kodara vanishing is useful in proving stuff in birational geometry. And so, for example, we were able to show this way that one can run the minimal model program in dimension 3. And so this was this joint work with 6 other people, BM, PS, T, WW, and also Yoshikawa and Takamatsu independently observed the same thing. In my notes, I will give a proper attribution where I say what the names are. And so I don't want to go into this direction. If you want to see more about the birational geometry applications, again, I suggest looking at Carl Schwede's talk from just this last Tuesday, where he talked about it.
Sorry, well, when you say number 2, the characteristic P version, are due to, so what does it mean, the characteristic P version?
So over here, I was living over ZP.
Yes.
If instead I was over Z mod P.
But what does torsion mean?
Oh, sorry, yeah, it just means everything.
Oh, I see, you kill everything. Okay.
You kill everything, right. Okay, so here's an exercise in understanding what the theorem is saying, if you're so inclined. And so it's a singularity in mixed characteristic. So it's a very explicit thing. So let me just write it. ZP is joint X.
Can I ask?
Yeah.
So for example, in the standard cyclic covering trick, part C appears as a direct summand. So this means your coverings are not of that kind.
Correct.
I see.
So if you see the proof, the coverings are constructed slightly inexplicitly, but the kind of thing you have to do is you have to, I'll come back to it at the end. It's about making things perverse on the generic fiber. And so you have to do something. The cyclic covering trick will not do the job. Yeah. And so here's the singularity. It's like the Fermat cubic, x cubed plus y cubed plus z cubed, except I replaced z with the prime number p. So it's some mixed characteristic version of the Fermat cubic. And so let's say S is spec R. And X is going to be the blow up at the origin. So I guess that means P, X, Y of spec R. And so again, the picture is the standard picture one draws in this setting. So this looks like a cone. And now I'm blowing up the cone at the cone point. And so I get a cylinder. Maybe I should draw this curve in red. So this is the curve that's being contracted. And this curve is in fact just the actual Fermat cubic. So this is the vanishing locus of x cubed plus y cubed plus z cubed, sitting inside P2 over Fp. Okay, so where am I going with this example? Where I'm going with this example is that this x is, if you try to compute what h1, so let me call this, this is an elliptic curve, so let me call it E. If you try to compute what h1 of the structure sheaf is for this x, it's actually isomorphic to h1 of E OE via the restriction map, oops. And so it's a one-dimensional vector space over the residue field, Fp. And so this theorem implies that there exists a finite cover such that pi upper star kills this class. Well, kills this entire group. And then the exercise is for you to try and find this cover explicitly without using the theorem. I spent a lot of time with this example in my life just to understand how to prove this theorem. And eventually when the theorem was proven, I don't know if there's a direct correlation between understanding the solution to this example and the theorem, but it was nevertheless useful to me. Right. Okay, so my plan for the rest of the talk is to sort of talk a little bit about the proof of this theorem. And really, I'll just focus on the first part. And really, I'll tell you the proof of half of the theorem. And that half is the half that uses the Riemann-Hilbert functor. And so that's why this talk is about the Riemann-Hilbert functor. Unless there are any questions before I start.
Can you recall what the Riemann-Hilbert functor means?
Yeah, I'll talk about it. It's well, in this context, it's something we define. So, So strategy of the proof. So there are two parts, and I will focus on the first part. Right, where did it go? Oh, okay. So I'm going to talk about Theorem Cm1, which means this local algebra theorem. Let me again scroll back up here. So I'm trying to prove that if you have this excellent Noetherian domain, then this absolute integral closure, this analog of the algebraic closure, is Cohen-Macaulay at all points of characteristic P. And we're going to do it in two steps. We're first going to prove it's almost zero, and then prove it's actually zero. So prove that H less than D at the maximal ideal of R plus is almost zero. And this is a technical term, which I will explain. So this is using the Riemann-Hilbert correspondence, or the Riemann-Hilbert functor. And then you have to prove it's actually zero. So that uses prismatic homology. And that part of the proof is, in some sense, I think the most difficult part of the proof, or the most subtle part anyways. And so there's no point in me trying to explain it in a short amount of time. I think the almost zero-ness is probably more useful for most people. And so this is today. The rest of today, really. Okay, and so let's, for the moment, forget about the statement. And let me just tell you what this Riemann-Hilbert business is. And then at the end, I'll try to connect it back to this vanishing discussion. So here's the Riemann-Hilbert. Okay, so what is Riemann-Hilbert? So classically, or from my perspective, classically, the Riemann-Hilbert correspondence is this correspondence. So if you have a complex algebraic variety and you're trying to understand sheaves on the variety with complex coefficients, so for example, local systems with complex coefficients, then Riemann-Hilbert says that you can understand this in terms of sort of differential data, like D modules, or vector bundles of flat connection if you are a local system, and then if you're a general constructible sheaf, then you do it in terms of D modules. So it's some process of taking topological input, like a constructible sheaf, and producing some algebraic output, like a coherent sheaf or a D module. But the topological input you're allowed to take in this situation is a Kiersig zero sheaf. So it's a sheaf with C coefficients. And so the question is, what do you do if you want to take in as input a sheaf with FP coefficients? Still on a complex variety. And that's what this p-adic Riemann-Hilbert functor I want to discuss is about. So setup is the same as what I've had in the previous talks. So C is CP is QP bar hat. It was this completed algebraic closure of QP.
Wait, I didn't understand the conundrum because you don't have the notion of a constructible sheaf.
We have the notion of a constructible sheaf.
Yeah, so what are you missing? Or what's the problem?
I want something on the other side. So I want some analog of like a vector bundle with a flat connection attached to a constructible sheaf with FP coefficients.
Oh, okay. The concepts are there. You don't have the construction.
Correct.
You didn't explain the construction in the first case anyway.
Right,
but we know it exists because we're our elders to tell it exists.
Right.
Fine.
But the mod P version did not exist, and so I was trying to motivate that. Yeah.
All right.
Right. And X over OC is something reasonable. So I don't know. Let me just say, finally, you can assume it's projective space for all I'm saying. Finally presented scheme, say. And then X0 is going to be X tensored over Z with Z mod P, or so, which is also the same as X tensored over OC with OC mod P. So I reduce the equations mod P, but not smaller powers of P. Okay, so this is the setup in which one in p-adic that one often finds oneself in p-adic geometry. And in the 80s, when Faltings was trying to sort of come up with what shape p-adic Hodge theory might take, I think one of his key innovations was this notion of almost mathematics. And that notion kind of crucially relies on the fact that this ring OC is not Noetherian. It sort of exploits the non-Noetherianness in a highly interesting way. So this is some huge ring. It's not Noetherian, but because it's not Noetherian, there are certain constructions you can do with it, which you can't do otherwise. And so here's the construction that he did. So construction of almost mathematics. So what he observed is that there's usually if you're working over something like a discrete value, like a PID or a discrete valuation ring, say, you can think about what kind of torsion, what would it mean for a module to be torsion? And there's really only one notion. It's killed by some power of the uniformizer. So it's killed by some power of P. But if you're working in this kind of infinitely ramified setup, there are two classes of torsion modules that one can have, and one is much smaller than the other. And so that's almost mathematics is going to kind of exploit this. And so let me, instead of just blabbing about it, just tell you what it is. So M inside OC is the maximal ideal. And the key observation is that this ideal is idempotent. So M is equal to M squared. And in fact, M tensor M is isomorphic to M, even in some derived fancy sense. So this is a phenomenon that doesn't happen in the Noetherian world. If you had an ideal in a Noetherian ring, which was its own square, it only happens for kind of stupid reasons, like it cuts out a connected component of the scheme. But not here. Over here, you have this. This is because M is sort of generated by all the p power roots of n of P. So it's the union over all n of the ideals generated by P to the 1 over P to the n for all n. And so what this means is, if I just look at M torsion modules instead of P torsion modules, so things that are killed by all small powers of P inside all OC modules, this category is actually a nice category. So it's a Serre subcategory is the technical term. Meaning it's closed under reasonable operations. Actually, it's closed under any operation you might imagine. So you can take direct sums, you can take extensions, you can take sub objects, you can take quotients, you can take arbitrary limits, arbitrary co-limits, etc. It's closed under all of these properties. And so in particular, what this means is that it's a reasonable thing to consider the quotient of this category by this category, which practically just means you just try and do usual algebra, but each time you see a module which is killed by this huge ideal, you treat it as 0. So the technical term is you call it almost 0. And so, again, what this means is that you can talk about mod OC almost, which is this quotient, and these are called almost modules over OC. And so the idea is that you've inverted a few more maps when you pass from the world of all modules to the world of almost modules. So for example, the inclusion of the maximal ideal inside OC is an almost isomorphism, even though it's not actually an isomorphism. But the inclusion of the ideal P inside OC is not an almost isomorphism. Does that make sense? So it's this kind of softening of commutative algebra over this highly ramified ring that we are going to exploit. And so, okay. And then there's a sort of version of this for things that are linear over OC. So there's also a version for, so I'll just say the fanciest version I need. So the quasi-coherent derived category of the scheme X0 in almost mathematics also makes sense. And you do the same thing. Every time you see something that's killed by this maximal ideal, you declare it to be 0. Okay, and so with this kind of definition, here's kind of a main theorem on the Riemann-Hilbert functor. Oh yeah, sorry, I should have said this. This was all joined with Lurie. It's in progress, but hopefully available very soon. And so what we prove is that there's a functor that produces, so there's this natural exact functor, RH, which goes from constructible sheaves, really the derived category of constructible sheaves on my complex variety with mod P coefficients, to quasi-coherent sheaves on my mod P object X0 in the almost sense. And so this is what I had in mind when I was saying I wanted to take as input something like a constructible FP sheaf and produce something that lives in algebra. So like a coherent sheaf, like a module. And it has a bunch of nice properties. So with the following features. So the first one is that it's compatible with proper push forwards in the sort of usual sense. So if f from y to x is proper, then there's a notion of push forward on both sides. I can push forward constructible sheaves along arbitrary maps, and I can also push forward quasi-coherent sheaves along arbitrary maps, and those are compatible with each other. So for the experts, there's no kind of funniness. Like in the D module theory, there's this D module push forward, and it's not literally the same as the O module push forward. That subtlety is not showing up over here, and I can comment more on that later. It's compatible with, so it has some finiteness properties. So the output isn't sort of arbitrary, but it satisfies the natural finiteness condition in almost mathematics. So for all constructible sheaves F, the object RH of F is almost coherent. So this is sort of the natural finiteness condition that one would encounter in almost mathematics. It doesn't literally mean that it's almost isomorphic to something finitely generated. Rather, what it means is that for every epsilon in the maximal ideal, there is some finitely generated module and a map between that finally generated module and your target module whose co-kernel is killed by epsilon. So it has kind of an analytic flavor to it. So for each epsilon, you require the existence of some finite amount of data, but there are sort of no compatibilities as epsilon varies. It's compatible with duality. So on the left-hand side, one has Verdier duality for constructible sheaves. On the right-hand side, after I make this coherence restriction, there's Grothendieck duality for coherent sheaves, and the two are intertwined by this functor. So RH composed with Verdier duality is Grothendieck duality composed with RH. What else? It behaves well on the perverse sheaves. So it interacts well with the perverse T structure in the following sense. So if I take something in perverse degrees less than or equal to 0 and hit it with Riemann-Hilbert, I get something in degrees less than or equal to 0 in the usual sense.
Sorry, Bhargav, can you remind me what is X over C? What are the hypotheses?
It's just any variety.
And C is the field, right?
C is the p-adic complex numbers, yeah. C is the usual C. Here, yeah.
However, at some point you reduce modulo P, right?
So, right, so X is something that lives in mixed characteristic. So it makes sense to take X and reduce it mod P.
Yeah, so usually when you learn étale cohomology, everybody says, be careful, take the prime invertible in the ring, but you're doing the opposite here.
No, my prime is still invertible in the ring, because on the étale side, I'm doing XC. So this is the generic fiber.
Okay. Mm-hmm.
So the picture is I have some family over OC. I do sort of constructible sheaves on the generic fiber, which is a complex variety. And the output is going to be some algebra object on the special fiber.
Okay, thank you.
Mm-hmm. Right. And then I was also going to tell you what it looks like in one example, but maybe that will probably not be that useful. So I will only do it if someone asks about it later. But I should at least make some comments on the theorem. So maybe first I should ask if there are questions, and then I'll make more comments.
Can I ask a question?
Yeah.
Will you say how does it compare to the classical Riemann-Hilbert?
Yeah, I will try to say something about that right at the end. But I want to sort of first explain why this implies this almost vanishing theorem that I mentioned before.
Did you say what RH was, the functor was?
I did not say what it was. I just told you what its properties are. Okay. It's a little hard to actually say what it is. So maybe let me not try and do that during the talk.
Okay.
It's like a complicated construction.
Is it correct to say that under this correspondence, perverse sheaves go to this quasi-coherent almost object?
Yeah, that is definitely true. Well, all sheaves go to quasi-coherent almost objects. Sorry, what do you mean? Maybe I didn't follow the question.
Now, just the last line suggests that if you reverse the arrow, then you get into coherent sheaves, right?
No. So then because of this property over here, if you reverse the arrows, you get into the Grothendieck dual of quasi-coherent things to the left of 0.
Yes, different, yes.
And so it's possible to refine the right-hand side and put a perverse T structure on it, and then say that the functor is actually T exact. But it sort of becomes more technical, so I just wrote down the simplest thing here. Right. So what I wanted to say, and I'll put this in the notes, but these properties over here, this one and this one, so the almost coherence and duality, these are sort of heavily inspired by work of Bogdan Zavyalov. He's a grad student at Stanford, finishing this year. So he proved Poincare duality for the mod P cohomology of proper smooth rigid spaces, rigid analytic spaces. Over the p-adic complex numbers, and the proof uses some of the same ideas that go into these statements, and in fact we were inspired to prove these statements because of his proofs. What else? Right, so okay, the other remark I wanted to make was the connection back to the original vanishing theorem discussion. And so, right, so if you take C and D, as Mark was saying, you can combine them, and what you learn is that if F is a perverse sheaf on the generic fiber with mod P coefficients, then if you do RH of F, and if you actually shift it by minus the dimension to sort of make it closer to constructible sheaves. Then you can, what part C and D together will tell you is that this object over here looks like the Grothendieck dual of a coherent sheaf that lives to the left of 0. And it's easy to see that that implies that this is actually almost Cohen-Macaulay. So this is some standard kind of commutative algebra fact that a lot of people have proven over the years. I don't want to attribute it to one particular person, but at least I've seen it in papers of Kashiwara and Gaber and Bezirkovnikov and Arinkin. And I don't know who the canonical source of this is, but it's this pure commutative algebra fact that if you take a complex of modules that lives to the left of 0 and Grothendieck dualize it, then what you get has good Cohen-Macaulayness properties. And so because of this, the almost vanishing theorem reduces to a very concrete statement about just perverse sheaves on complex varieties, which I'll formulate. So the almost vanishing in this theorem Cm reduces to the following. And so I'll say it as a proposition. It's really an exercise for people that know what perverse sheaves are. And so here's the exercise. So let's say Y over C is an irreducible complex, irreducible variety. Pi from Y plus to Y is the absolute integral closure. So the direct limit of all finite covers. And then the proposition says that if you look at the push forward of the constant sheaf Fp shifted by the dimension of Y, then this guy is actually imperverse. I mean, it's not actually perverse just because it's infinite type, but it's actually a direct limit of perverse sheaves. Okay, and so I don't want to prove this theorem, but the rough idea of the proof of this almost vanishing theorem is you first prove this proposition, and then using this proposition plus how the Riemann-Hilbert functor works, you immediately conclude that this R plus ring is actually the Riemann-Hilbert partner of something perverse, and therefore it has good almost Cohen-Macaulayness properties. And so that's kind of how the vanishing theorem goes. What I wanted to explain in this talk is that you need to sort of exploit some purely topological facts on the generic fiber. So just facts in complex algebraic geometry, and then hit it with this Riemann-Hilbert functor to get some conclusions in commutative algebra. Okay, so are there any questions about that? So then my plan for the last 5 minutes is to explain how this relates maybe to things that are more familiar from Kersig 0 that people might have seen before, called Riemann-Hilbert. But before I do that, are there any questions about this rough strategy?
So can you say in a couple words in the proposition what happens? For example, if Y was very singular and pi is the identity, you definitely don't have that it's perverse. So
right.
What happens in the limit? What?
Yeah. So somehow, so what is the obstruction to a sheaf being perverse, right? Let's talk about half of it. So if you want to figure out whether or not something is, let's say, in perverse bigger than or equal to 0, the obstruction lie in the shriek stocks at the various points. So I need to sort of pick a point of the singular locus, look at a small neighborhood of that point, remove the point, and try to understand the local singular cohomology of that ball. And so what this theorem is saying is that even though those local étale cohomology groups might be non-zero, you can find finite covers where they become 0. So it's the same kind of cohomology killing statement that showed up earlier, but now in this kind of étale world.
Is the finite cover branched?
Yeah, definitely. Because again, the statement is interesting for simply connected varieties, or you want a statement for simply connected varieties, so you better allow branch covers. Yeah. And I think somehow, like morally, at least the idea is that the more ramification you allow, the more vanishing you get. And this is some way of making that precise. Okay, so let me talk about this Kersig 0 version, and then I'll stop. So there exists a version. So I said everything with FP coefficients, but you can always, so first of all, it works with Z mod P to the N coefficients, and then you can take a limit and invert P. So there exists a version with Z mod P to the N coefficients or QP coefficients. And the QP coefficient version has a refinement, which I want to write down. So the latter has the following refinement, which is related to Saito's work on mixed Hodge modules. Oh, I think it is. I'm not an expert. But so here's the expected theorem. And I say expected because this part is less written than the previous part. The previous part is more or less written. So we expect to prove the following. So let's say X over QP now, over the small field, is an algebraic variety. I'll say smooth because I want to say it in terms of D modules, but you don't have to do that. So I have a smooth algebraic variety over the complex numbers, or the p-adic numbers. Then there exists a natural subcategory, PB cons WHT. So it's what we call the weakly Hodge-Tate constructible sheaves inside all constructible sheaves. So it's an additional constraint that a constructible sheaf has to satisfy. I apologize. Sorry. Let me write it properly. So, okay. This is the category of all constructible sheaves on X, and this is the subcategory of weakly Hodge-Tate sheaves. There's a natural subcategory, which is stable under all geometric operations. Meaning push forward and pull back and so on. And on this subcategory, the Riemann-Hilbert functor is related to filtered D modules in a nice way. So plus a commutative diagram, which looks like so. So here's this weakly Hodge-Tate category with QP coefficients. First thing I can do, well, let me go this way. So we expect that there's a refinement of this RH functor, which I'll call RHT, which goes to good filtered D modules. In the derived sense on X. And if you have a good filtered D module, you can look at its associated graded. And what you get is a graded Higgs sheaf on X. So this is another way of saying the PB co of the cotangent bundle, T star X, or the graded version thereof. Now, if you have a graded Higgs sheaf, so if you have an object that lives on the cotangent bundle, you can restrict it to the zero section of the cotangent bundle. And if you do it in the derived sense, oops. So let me call this zero upper star. So pull back to the zero section. What you naturally get is a graded Hodge complex. And so what do I mean by this? What I mean is a module over the Hodge complex. So just the de Rham complex with the de Rham differential turned off. So just omega I in degree I, but zero differentials. And it's again coherent and it's still graded. And if you have such a thing, I can further extend scalars to the p-adic complex numbers. So that's just tensoring with C. Omega I xc based in degree minus I. And this functor, this vertical functor you get over here is the RH functor I talked about before. And so the assertion I'm making is that on this subcategory, this RH functor that I was just talking about before actually has a refinement that lands in filtered D modules. So you can take a constructible sheaf and produce a filtered D module functorially out of it. And in particular, what this means is if you sort of know interesting theorems on this side, you can just hit them with this functor to get theorems on this side. And one example of something like this is that you can prove the decomposition theorem for filtered D modules this way. Because for filtered D modules, a geometric origin this way, because you can sort of prove it on this side just using PBDG. the Valence and Bernstein-Deligne decomposition theorem for constructible sheaves, hit it with Riemann-Hilbert, and you get the corresponding decomposition for filtered D modules, and therefore also for the corresponding Higgs sheaves and the corresponding Hodge complexes. And so this gives you a p-adic way of proving, for example, Collar's vanishing theorems on the behavior of the canonical bundle under proper surjective maps at smooth source. And so this is something we're still working out, but I believe this is the correct picture. And so this is the relation between this kind of Kirsig P Riemann-Hilbert that showed up in this vanishing theorem discussion in this kind of slightly fancier version. Okay, I think I'm about out of time and also out of things to say, so I'll stop here.
Okay.
Questions?
Next question. So here, this good filter means in the cycle sense, right? It's like on the vanishing cycles, the nearby cycles they have.
No. There's no condition of vanishing on nearby cycles. I just mean filtered D modules whose associated gradient is coherent over the cotangent bundle.
Other questions?
What's the use of, you mentioned the decomposition theorem on the good filter D modules. What's the use for that?
Well, so my impression is that that's one of the sort of, it's one of the important applications of Saito's theory of mixed Hodge modules. Like I think when he was trying to prove these, Collar had these theorems on high direct images of the canonical sheaf. And I think one of the early applications of Saito's theory was reproving them through mixed Hodge modules. And I think the special case that gets used is exactly the good filtered D modules that come from geometry along like a proper map. And the reason you care about it for the filtered version rather than the D module version itself is I think my impression is that the more interesting applications from the algebra geometric point of view are on this side. You care about the decompositions you get at the level of Hodge complexes because the canonical bundle shows up as a direct sum end over here. And so you really need this kind of filtered refinement for that. Like you can't use classical Riemann-Hilbert.
And that's another question. So here, you know, this RH hits into the good filter case. Is that because somehow we're at positive characteristic? I think something are naturally filtered rather than in the.
So this is something I mentioned in my first talk that I might come back to, which I guess I did. So it's because the Galois group is involved. It's because the Galois group with the p-adic numbers is so big, it acts on everything and it produces things naturally with the filtration, unlike the usual complex numbers.
Yeah.
And it's more precisely the wild part of the Galois group that gives you the filtration.
Yeah.
So you said you can make your Riemann-Hilbert functor T exact. Can you describe what the T structure on the coherent side is?
Right. So I said I can make it T exact if I refine the target. So one thing I didn't say about what this functor does is that I didn't say what it does to the constant sheaf. It doesn't go to the constant sheaf. Rather, it goes to something called the perfectoidization of the constant sheaf. So using prismatic cohomology, you can define this notion of perfections in mixed characteristic. And the constant sheaf goes to the perfection of the structure sheaf. And then what I'm saying is that if you work with modules not over X naught, but rather over the perfection of X naught, then there is a natural perverse T structure on that guy. And the functor is T exact.
Is this some kind of middle perversity thing or something else?
Yeah, it's middle perversity.
Middle perversity, okay. Thanks.
So the perverse co-connective guys, the stuff that's to the right of 0 is defined by a condition on the Schrieg stocks. And then the connective guys don't have an explicit description.
Bhargav, so I mean, I realize this is totally not a realistic question, but I mean, can you give some, again, just some heuristic for, I mean, it seems sort of magical that you can go from some topological thing over C to some algebraic information on the special fiber. So just sort of what kind of thing is involved in going from one side to the other without sort of
without telling you what actual construction is.
Right. Is that possible? Or?
Well, it's kind of a push forward. So somehow, like if you accept the theory of rigid analytic spaces, so okay, let me give you at least some heuristic. This is not going to be a proof of anything, but if you have sort of X over OC, which is the scheme in mixed characteristic, what you can do is you can look at the scheme. Let me write it over here. I can look at the scheme theoretic generic fiber of X. It maps to X, but I also have the formal scheme, the formal completion of X, which maps to X. And so the formal completion is something that sort of more or less depends on the special fiber. I mean, the topological space, for example, is the special fiber. And then here's the analytic space attached to X. So let me maybe assume X is proper for this discussion. And so the analytic space attached to X maps to, attached to the generic fiber maps to the generic fiber, but there's kind of a natural map in this direction, which is called the nearby cycles map. And so what happens is that you take your sheaf over here, you pull it back over here and push it forward over here. I mean, it's not quite that construction, but that's roughly the idea for going from stuff on the generic fiber to stuff on the special fiber.
Oh, I see. Okay, so
it's some kind of a nearby cycles operation.
Okay. Yes, you're still kind of thinking of it as a family where the thing over OC sort of is the generic thing, and then the characteristic P thing is the special fiber.
Right.
Yeah, this is very.
I mean, so the thing that came as a slight surprise to me was that like doing nearby cycles in this mixed characteristic setting, like literally is a bad idea because it produces like infinite dimensional things. But somehow if you do this kind of a tweak, so the actual formula is you take a sheaf over here, you pull it back over here, and then you tensor it with something over here to make it coherent. And then you do the nearby cycles. Then it actually turns out to produce a reasonable object. And it's that tensoring step that's, I think, kind of surprising maybe.
But so these nearby cycles, they live in some kind of coherent world. Now, they're not topological things, but.
It's because I'm tensoring with something coherent. So if I have a sheaf F over here, what I'm saying is I send it to, first I do the pullback pi upper star of F, then I tensor with something that looks like a structure sheaf. It's not quite the structure sheaf. It's some decorated version of it. And then I push it forward. And it's because of this O over here that you end up producing something coherent.
Okay.
And this is something you can only really make sense of in some, well, I'm still lying a little bit, but you really have to pass to some kind of a pro-étale site and perfectoid spaces over here. So something further up here to make sense of this sheaf. But that's kind of the glue that goes from constructible to coherent.
Okay, thanks.
Can you say what the map nu is?
So, well, it's a little hard. So there's this.
No, just roughly, intuitively.
Okay, intuitively, what are points of this space? So points of this space are given by, like, if I have a C-value point of this space, then what the map is basically saying is that you look at, so I don't know if you're going to like this, but it's using the evaluator criterion of properness. So if you know where spec C goes, you also know where spec of OC goes, and therefore you know where the special fiber goes. And you look at the image of the close point under that map. Another way of saying it is that there's this, so in this world of adic spaces, which is what we use, there's a way to describe the generic fiber in terms of the formal scheme as the inverse limit of all the blow-ups of the formal scheme. And then the map is just the projection map.
Okay, thank you.
So this tensor tensor operation here, is that like in the D module direct image, you need to tensor with the transfer module?
Maybe. I mean, I'm tensoring something constructible with something coherent. I thought you don't do that kind of thing in the classical framework.
I just like it formally looks so.
Right. I think the thing that's slightly weird about this is, like if you, in algebraic geometry, if you did some operation like this, you would produce garbage because you would not get something quasi-coherent. Like it wouldn't be compatible with localization. But somehow, because of the completions involved, it ends up being quasi-coherent, and that's what makes sort of the tensor product a reasonable thing to do.
So I have a vague question. You know, like flying in an airplane above all of this. The perfection process, well, somehow there's this inverse limit of Frobenius in the perfectoid process. And why is that becoming a panacea and solving lots of issues? It's a very general question.
I
mean, just
well, it tends to rigidify things for one thing.
Rigidify, yeah.
Like if you have like two endomorphisms that you're taking inverse limits of, and those two endomorphisms are p-adically close to each other, then the inverse limits are actually isomorphic.
Yeah. Okay.
So that rigidifies things to some extent. I don't know if that's the reason.
That's you know, that fits with my intuition about what inverse limits are doing. Yeah.
Mm-hmm.
It happens in dynamics. So it tends to rigidify and simplify in some sense.
Right.
I know you mentioned X proper, but going back to the general thing of Kodaira vanishing, how does it fit in here? I mean, of course, X0 is a characteristic P, so you don't have it. But do you have, what happens to our thin vanishing theorem in this pull back, push forward process, or other cohomological questions? And
let's see, do I follow? I mean, one thing that happens is like this perversity statement up here. Where is it? This more or less does come from some version of Artin vanishing for perverse sheets. But maybe I didn't follow your question, sorry.
You see, if what I was asking is that that's a general thing that has nothing to do with XC being affine, right? But somehow you're saying that you may use an Artin vanishing theorem to prove that inequality. So let's say that XC is affine.
Okay.
So you expect some vanishing for a perverse sheaf, right?
Mm-hmm.
What's the reflection of that in X hat, in X0?
It's this fact. That's exactly this fact that I was saying. So the reflection of that in X hat is that the perfection, so I didn't tell you what the perfection in mixed characteristic was. In characteristic P, any ring has a perfection and it's a ring. In mixed characteristic, there is a notion of perfection, but it's not a ring, it's a derived object. And the answer to your question is that if the generic fiber is affine, then the perfection in mixed characteristic satisfies a version of Artin vanishing. So it goes from 0 to the dimension rather than beyond that. So it's about the cohomology of the perfection.
I see, the complex itself goes
right.
from 0 to the, yeah.
Well, let me then see if there are any.
I have one more question. Wait. So in the interest of economy, given that we have this, given that we had the discussion, the informal discussion before, that you haven't really defined the prismatic cohomology. Mm-hmm. Given the discussion before, there's a certain site and construction which is analogous to the Czech cohomology construction. So of sheaf cohomology. If we just replace topological space by site and define what the prismatic site is. So so the question is, what is the thing I have to learn to understand the construction of prismatic cohomology? It's just a prismatic site, right?
Right. It's just the definition of, with the prismatic site. And then you said the right words after that to get to prismatic cohomology.
Okay, fine. Mm-hmm. Okay, so what's the, okay, so you can start me off now. So what is the prismatic site, but say it in, sort of a kind of a fast way.
Well, I tried to say it, right? It's like these one parameter deformations that carry a
You did
Frobenius.
say it, yeah, right. Okay. So say it again. Say it again.
So you have your scheme X and you try to probe your scheme X by things mapping into it. But the things mapping in aren't arbitrary schemes. They're schemes that are equipped with a one parameter deformation whose total space carries a Frobenius.
And you just consider all maps. But what is the?
So that's a prism over X, and those are the objects of the prismatic site.
Right, but how does this extra structure on the domain fit with the dome? How does the range?
There's no compatibility between the extra Frobenius structure on this deformation and the map.
Oh, you just probe. It's like you just you
there is some restriction on what I mean by a one parameter deformation. So the deformation has to interact with the Frobenius in a very specific way, which is this prismatic condition.
Okay. All right. So then you just take all maps in the category of schemes.
Yep.
And with the coverings, which ones?
If you're working with affines, you don't need anything. You can just work with the indiscrete topology. And then otherwise you can do something like the Zariski topology on the source scheme mapping in. The theory is like a coherent theory. So it's the same kind of thing that works for coherent cohomology. So for affines, you don't need to do anything. And then for general schemes, you do Zariski topology.
So it's a big site.
It's a big site.
Can I ask a vague question? So in the description you just mentioned, is it like looking at the loop space of the variety, but the loops you take has something to do with the Frobenius? Well, I don't know if this makes sense at all.
I haven't thought about that analogy. Somehow, okay, this is kind of bullshit, but my picture of what like a prism over X is, it has to do more with F1 rather than with loops. So somehow to me, like if I have, so spec R to X, and then I have this deformation spec R tilde, which carries a Frobenius. So such an object is an object of the prismatic site of X. And somehow morally, this is supposed to correspond to a map from spec R to X, but only over F1.
What is F1?
The field with one element. As I said, this is bullshit. It doesn't really make sense. But
okay. No, I like bullshit.
That's kind of what motivated this. Well, I mean, it lurks in the background that this kind of one parameter deformation has to do with this fact that spec Z is one dimensional over F1.
And then this extra structure, of course, comes in when you form intersections of open. Mm-hmm. And so that's where it comes in. Sometimes.
Right, exactly, yeah.
Okay. So what do you see for the future?
Do I see for the future? Well, wait, of what? Of the world? I'm not that hopeful.
No. There's a new tool now.
Right. So
in
terms of this prismatic stuff, the thing that has not yet really been seriously studied is the absolute theory rather than the relative theory. And so the stuff that I talked about in these lectures uses the relative theory in the sense that you fix the prism you work over and everything happens sort of over that. But there's an absolute theory where you don't fix the base prism. And that seems to have some kind of interesting implications in arithmetic, which are still being developed.
What would that be analogous to in normal things where you don't fix, it's like you don't fix the field of your variety is over?
Kind of like that, yeah.
Huh? What?
Well, a prism structure is more like a descent of the base to F1 in this analogy. And so I'm not fixing that descent anymore. So I'm looking at all possible ways of descending it to F1.
But can't you make a less BS analogy to an analogy. The BS is in the analogy now. Make an analogy to something a little more real.
So I don't know examples of naturally occurring sites which don't have a final object. I mean, the crystalline site is one example, but that's perhaps the simplest example of a site which doesn't have a final object. And what I'm trying to say over here is that the absolute prismatic site does not have a final object, and that actually makes it like an interesting thing to think about.
It's like, is it sort of like considering spaces or spaces without base point, with base points, and spaces with base point, without base points?
Okay, maybe in terms of analogy, it's like saying you want to talk about a manifold, but you somehow are not allowed to talk about a manifold. You're only allowed to talk about the contractible opens inside the manifold. So you have that poset, but you don't have the manifold itself.
Well, you haven't made the
somewhat right.
You have the category of open.
Right. I mean, of course, in this case, you can just say take the colimit over all those opens and you recover your manifold. But somehow, I think that's roughly what I'm trying to say over here.
Oh, okay. Well, no, that makes a lot of sense to me, because sometimes you can't really take the colimit. And okay, I see. Okay, thank you.
And what's an arithmetic application that people may want to pursue?
Okay, so you can talk about the absolute prismatic site of just ZP itself, spec ZP. And this turns out to be something quite interesting. So how do I say it? So, okay, there's this notion of a crystalline Galois representation, which is very important in number theory. It's some like integrality condition on the Galois representation, except it's only defined with QP coefficients. And we don't have a good notion of a mod P crystalline Galois representation. And one candidate application of this prismatic stuff would be that a crystal on the absolute prismatic side of ZP would be a candidate definition for an integral crystalline Galois representation. And so for people that want to do things like deformation theory or Galois representations, this definition could be useful.
Oh, I see. So I can generalize that. I mean, there are many things that work nicely in crystalline for smooth things, but there are always these sometimes there are always these denominators. And then you're saying you can extend possibly some of these nice things in the crystalline theory to either similar things or do them over ZP better than.
Right. I think it's the doing them over ZP part that I was alluding to.
But you can also add singularities to some of the nice things in the crystalline theory, right? That only work.
Right.
Right. Oh, okay.
I mean, okay, one thing I always wanted to do is there's this analogy between 3 manifolds and spec Z, right?
Yeah.
And the analogy is like spec Z is like a 3 manifold, and then spec FP is like a knot inside the 3 manifold. And then like a little kind of solid neighborhood of this knot is analogous to spec ZP.
Yeah.
And then the boundary of that solid neighborhood, which is a Riemann surface, is analogous to spec QP.
Yeah.
And so if you take this analogy, then you can sort of study local systems on the 3 manifold, and you can restrict them to the Riemann surface. And you can also take local systems on sort of the solid tubular neighborhood of the knot and restrict them to the Riemann surface. And on this topological side, you can prove that the moduli of local systems on a Riemann surface is symplectic, and both of these are Lagrangian inside there, which gives you some kind of a 0-dimensionality statement for the intersection. And the hope is to do something similar in the arithmetic side. Now, if you're able to do it, you would prove some amazing conjectures like the Fontaine-Mazer conjecture. So I think we're quite far from this. But what this prismatic stuff lets you do is allows you to make sense of 1/2 of it. So it allows you to make sense of restricting local systems from the solid tubular neighborhood of the knot to the sort of boundary of that solid tubular neighborhood of the knot. And so you can like formulate what it means for this restriction map to have this Lagrangian image. And that turns out to be true, and it's sort of closely related to some to the Balens and Lichtenbaum conjecture, for example. So there's like more things to do in the arithmetic direction if you play around with the absolute prismatic side. But this was one example.
And this picture is exactly, well, it, you know, in first in topology and then later in symplectic topology. I mean, Casson made these great invariants by considering the Hegardt decomposition and considering considering representations on each of the tubes. Then the manifold looks like two neighborhoods, but not of a single curve, a single circle, but of like a graph, like a tube around a graph. And then every manifold is the union of two such things. And there was the Casson discussion where he considers representations of these free groups and then restricting them to the Riemann surface. And there were two Lagrangians inside the space of all representations, which had a symplectic structure. And then the intersection number was the famous Casson invariant. And then that generalized to what's called Hegardt floor homology and symplectic topology. So this idea is very much, so you're saying kind of half of the story could be enhanced with prismatic considerations when you go to arithmetic and form these pictures from arithmetic. Who's the first one to make this analogy? I mean, I heard it from Barry Mamazer in the 70s.
Yeah, I mean, he's the person I would think of. I would think of Barry, yeah.
Oh, Barry is probably the one, okay. So what about the other half, though?
The other half has to do with the global field. So everything we're talking about is kind of p-adically completed. So that sort of corresponds to the solid tubular neighborhood of the knot mapping to the global one. I think we're far away because I don't know. You need to deal with the Archimedean place.
Well, there is a symplectic topology going on. I mean, I've been trying to convince them that they're Archimedean. They have to think non-Archimedean, and so you could walk over there and tell them what they have to do. I mean, they don't know about geometers don't know about the non-Archimedean completions, right? It's some other crazy world.
Right.
Well, I enjoyed the lectures. Thank you.
No, thank you. Thanks for the discussion.
Good. Well, I hope you've enjoyed your visit to
I did. Yeah. Thanks.
Thanks again for coming. And
yeah, no, thanks a lot for having me. It was fun.
Thanks again. Bye-bye.
Bye, Bhargav.
Bye, everyone.